Hello, everybody. My name is Nicholas Cosello, and I'm going to talk to you guys about how we're going to use infrared spectroscopy to study HCl and DCl. Just a quick review on what HCl and DCl are. If you're doing chemistry and you don't know what HCl is, I'm very surprised. But DCl is the same thing, except for instead of just having a proton and a neutron in a hydrogen atom, proton and electron in the hydrogen atom, you're going to throw in a neutron in there as well. And since we just have a proton and electron in the hydrogen and then an extra neutron in deuterium, that's going to be a pretty big difference in mass, and we're going to want to see how that difference in mass affects certain properties of the molecule. What properties in particular? We're going to talk about the vibrational and the rotational properties of the atom, so of the molecule. So we know that as the molecule is existing just normally, it isn't static. There's a lot of vibrations, a lot of rotations that's happening there. And so I have a nice little model to show of the vibrations to start off with. And we see that that bond connecting them is stretching and collapsing. It could be happening at this speed, or it could be happening faster. The difference being energy. As you put more energy in, it's going to stretch and collapse faster than that. And so what we need is a model to talk about, how those transitions work, right? And so we have one called the harmonic oscillator model, which talks about the different levels of speed of it vibrating as different discrete energy levels, called V equals 1, V equals 2, V equals 0 for the ground state, so on and so forth, right? Now, this is a really nice model, and it helps us really, it's going to give us our calculations, and it's going to do a lot of things for us, but it's not entirely accurate, right? What we really see is something like this, and this should make sense, right? At really small bond lengths, you know that you have, the molecules are going to be repulsing each other a lot. They have a lot of repulsive forces, and so energy is going to skyrocket. By a really high bond length, they're just really far apart, not interacting with each other at all. So energy is not skyrocketing; it's just tapering off. And this, asymmetrical curve is very different than the symmetrical harmonic oscillator model. And the difference between the two is called aharmonicity, and it's going to depend on a couple of things. But as we deviate from the harmonic oscillator model, some of our predictions are going to turn out to be not true. Now, we're going to just apply a lot of the same things to rotations. Instead of vibrating, it's just rotating. And the different speeds of it rotating are described by different rotational energy levels called J equals 0, 1, so on and so forth. And one thing to keep in mind is that it's much easier for it to rotate than it is for it to vibrate. It just requires less energy to do those transitions. So how are we going to capture this? We're going to do spectroscopy, which means that we're going to point light at our analyte and see how it interacts to that light. And the different wavelengths of light are going to do different things for the molecule. So if we're talking about just radio waves, we're talking about maybe NMR. But if you're talking about microwaves, then you're just talking about the rotational. So a molecule will absorb light in the microwave region when it wants to promote to different rotational excitances. But we want to do rotational and vibrational. So we're going to look at the infrared region, IR. So how are we going to do this experimentally? Well, HCl and DCl are gas. We don't want any other gas mucking up our values. So we're going to take a vacuum line. We're going to suck out all the gas. And then we're going to get HCl and DCl in our vacuum line, which is going to include our IR cell. So you're going to pinch off, so it just has HCl and DCl in it, and it is sealed. Then we're going to shine infrared light on it. And when it absorbs our infrared light, it's going to be when there's different vibration and rotational transitions happening. And it's going to let us analyze those different transitions. So this is what we get from it. Go ahead and ignore the first peak in between 1,000 and 1,500 wave numbers. It's junk. It's just picking up on something it's not supposed to. But we see that two of these peaks are much higher than two of the other peaks. That is because in the harmonic oscillator approximation, the only transitions that are allowed are the change in V must be plus or minus 1. But since we're deviating from the harmonic oscillator, we're actually seeing two overtone transitions down here, which are going from the ground state to the second state. This is classically forbidden. The chance of it happening is not very high. This is why its absorbance is lower than the other two, but we're still seeing it. So these are going to be our V from 0 to 2, and this is going to be our V from 0 to 1. But we know that we have two molecules here, one of them HCl, one of them DCl. So which one's which? If you look at our formula for our vibrational energy levels, you're going to see that depends on mass. So we already know that deuterium is much more massive comparatively to hydrogen. So as you see from this formula, as the more massive molecule is going to absorb at lower wave numbers. So we're going to have this guy being deuterium versus this guy's hydrogen. I'm going to go ahead and mark everything that I just said there. But notice that I haven't talked about rotations yet. This is just all vibrations. So what are rotations? We have to zoom in a little bit for that. So I'm going to go ahead and zoom in on our DCl 0 to 1, or as DCl fundamental versus DCl overtone from 0 to 2. So if we zoom in our DCl fundamental, you can see here that we have a whole bunch of different transitions going on inside of our vibrational transition from 0 to 1. And these are our energy level transitions, right? So from this guy is going from J equals something to J equals something. It's absorbing energy to go to a different rotational energy state. There are a couple things to point out here. One of them is that we do have some splitting here, and that's because chlorine also naturally has two isotopes that we see. But since the isotope, or the difference of a couple of neutrons is going to matter much less for chlorine than it does for a small atom like hydrogen, the split is much smaller. So we really just kind of see it at the rotational level and, just very small. Now I want to talk about the general curve here. The curve means from our Boltzmann constant, from a Boltzmann equation, we know that different transitions depend on the likeliness of the transition happening. Depends on the population of the place before the transition happens, and the energy it takes for that transition. So if we look down here, we're at really it doesn't take much energy. So you would almost intuitively think that this guy should be really likely to happen. But at a room temperature, we're already at the higher energy states of rotational energy levels, because it doesn't take much energy. So there just isn't much to start with here to transition, which makes it just an unlikely transition to happen, rather than say here, where it is a higher energy, but there's much more in the population there at room temperature. So then as we go on, energy starts to take over, and it just becomes less likely to happen. So that's why we get these general shapes. Now notice that we almost have a different branches here, right? We're going to call this guy the P branch, and that's where you are going from J to the change in J is -1. So you're going from J equals 2 to J equals 1, for example. Over here, the opposite's happening. We're going from, we're going to call this the R branch. We're going from J equals, let's say, 0 to 1, so +1. Now, right in the middle here, you have our Q branch, which is J not changing, which is forbidden by our model. Now, Nick, you might be saying, the overtone transitions were also forbidden, but we still saw them. So what's that about? Well, as I said, we deviate from our harmonic oscillator model more than we deviate from our rotational model. So that deviation allows the overtones to exist and be measured, but this doesn't for this particular molecule. So we just don't deviate enough for to see the predictions becoming incorrect. Now, what are we doing with this? Well, there are a whole bunch of different constants and a whole bunch of different values that describe how the molecule, essentially, how it rotates, how it vibrates, all of these things. So we are going to want to talk about those and measure those. So how do we do that? Well, we know that these constants, such as V sub E, B sub E, A sub E, and D, as you see here, are all part of the dependence on the wavelength of the transition with this J value. So if we go ahead and we graph out within a specific peak, that relationship and fit it to a cubic function, you can get these values. And by inspection, you can say, okay, well, for D must be 0.0016, so D must be 0.004. And if you go do that and do that for all of them, you get these first couple here. And then by definition, the distance between the two atoms, can be found with these guys, just with their definitions, the force constant, all these things, the bond enthalpy over here, because B describes how easy it is for it to rotate, and then this is the distance between your molecules, and then this is your vibrational frequency, and so in force constant. I don't know if I said that. But all these things have different physical meanings, and so it's really important to know how that varies from HCl to DCl. And not only that, but we can also see the relative intensities of these peaks by this formula. And since it's only proportional, we can only do the relative intensity. But if you do that, you can see here that if you just pick the first four, the relative intensities are a little bit different for HCl and for, this is for HCl, so for the different P and R branches. So in terms of discussion, what we see is that the mass affects your wavelength, the absorption of the wavelength or the wave number, they're inversely proportional, affects your rotational constants and some of your other physical constants. One thing that doesn't affect is your bond length or your force constant. As we saw, those are really close to each other across HCl, DCl. And this is very important because depending on what we want a molecule to do or we're trying to observe, making isotopes or observing different isotopes can change some of these constants pretty big. The rotational constant was almost double. So yeah, it could definitely matter in some cases. All right, that's all I got. Thank you for watching.